model. This example is for the 0 to 50% input region, and I'm just going to kind of scroll through these, but you'll notice that as the KC increases, the offset decreases, which supports the statement that an infinite KC yields no offset with proportional only controller. And there you can see the oscillations never settle out, giving you the marginal stability, ultimate KC. The results for all of the modeling proportional controller models are shown here, and you can see a steady increase for each region in the KC values, that's how the models are run, and the settling time shows a similar behavior to the KC values. So as the settling time, generally as the KC values increase, the settling times increase as well. As I mentioned about the offset is decreasing until we show no offset for the ultimate KC values. These are examples of the experiment part of the proportional controllers, proportional only controllers. This is for finding this is for the 80 to 85% input region, and this is how we found the critical damping. We found it to be 0.15% per volt for KC. This is for the quarter decay, and this is for the ultimate decay. And you see the oscillations never settle out, and you don't have a decay ratio. Here are the results for all of those regions for the proportional only controller experiments. Next, we went into doing proportional integral root locus, and that helps us determine the design KC values. The root locus is done by real and imaginary parts, and once that plot is created, you can draw 0 degree, 45 degree, 70 degree, 78 degree, and 90 degree lines and see what values of KC gave you these data points along the intersections of those lines. The results of those for critical damping were the 70 to 80% region showed almost no KC for the critical damping, and you can see Thomas's region shows significantly greater KC values for the critical damp, and also we wanted to compare what happened when you multiplied the tau I by 4 and divided it by 4. We wanted to see how those results would change for KC values. This is the 1 500th decay for these experiments, the 1/10th decay. And it's interesting that when you look at the tau I, in the blue, it's smaller than the tau times the 4 here, and then significantly, smaller than tau I times 4. But when you divide the tau by 4, that's quite a dramatic decrease in your KC value that's given. And that happens consistently through the ranges. And it's the same story for the quarter decay. See that initial tau value, little step up to the tau I times 4, and then dramatic decrease in the tau I divided by 4. And same with the ultimate KCs. In conclusion, we looked at the system. We reviewed all the work that's been put into the system in determining the characteristics through the SSOC, the Bode diagrams, the step response, the sign frequencies, the root locus, and the proportional only controllers, and we introduced what we have done to design a proportional integral controller. Does anyone have any questions?
And that's for Tim, and this is for Thomas. Did we clap for you, Dylan?
Nope.
Dylan? John, do we clap for you?
Yep.
You sure?
Do it again.
All right, just in case he remembers differently, I just don't remember. Just in case, make me happy, let's clap for John.